Hello and welcome to Insight Ophthalmology. In the previous modules, we discussed two important aspects of intraocular lenses. In Module 1, we discussed the materials used in IOL manufacturing. In Module 2, we discussed the IOL designs, including the optic and haptic configuration. And now in Module 3, we will move on to another very important concept in cataract surgery, that is the focality of the intraocular lenses. Before we start discussing different types of intraocular lenses, let us first understand a very basic concept, that is focus. When light enters the eye, the optical system of the eye bends these rays so that they meet at a particular point on the retina. This point where the light rays meet to form a clear image is called the focus. Now, different optical systems can create different numbers of such focal points. Some lenses create only one focus, while others are designed to create multiple focal points, allowing a person to see clearly at different distances. The ability of a lens to create one or more focal points is what we refer to as the focality. So in simple terms, focality describes how many points of focus a lens can produce inside the eye. Understanding focality is important because it determines how a patient will see after cataract surgery, whether they will see clearly only at distance or at multiple distances. Based on the way they create focal points, intraocular lenses can broadly be classified into three main types. Monofocal IOLs, these lenses create a one single focal point, and usually this focus is set for distance vision, which means patients often require glasses for near vision or reading. Then we have the multifocal IOLs. These lenses will create multiple focal points. This allows the eye to focus at more than one distance, such as distance or near, or sometimes distance intermediate and near as well, based on which multifocal IOLs can be bifocal or trifocal IOLs. Then we have the extended depth of focus IOLs or the EDOF IOLs. Instead of producing separate focal points, these lenses create an extended continuous range of focus. This allows the patient to maintain that useful vision across a range of distances, particularly the distance and intermediate. In addition to these, there is another important category called the toric IOLs. The toric lenses are designed specifically to correct the corneal astigmatism. They do not change the focality of the lens, but rather correct the cylindrical power of the cornea. Now, because of this, the toric options can be combined with monofocal lenses, with multifocal lenses, and even with EDOF lenses. Okay, so far, what we have discussed is a basic conceptual overview intended primarily for the beginners. At this stage, the goal was simply to understand what focality means and how intraocular lenses can be broadly classified based on the number of focal points they produce. From here onwards, we will gradually move into a greater depth. The next part of the lecture will cover the intermediate level, where we will begin to understand how each type of intraocular lens actually works from an optical standpoint. Then we will discuss the design principles behind monofocal, multifocal, extended depth of focus lenses and understand how these designs influence the visual outcomes. Finally, towards the end of the video, we will move into the advanced level where we will briefly review some of the commonly used intraocular lens platforms currently available in the market and their key design specifications. Before we discuss these lenses individually, it is useful to understand an important concept used in clinical research to evaluate their optical performance, that is, the defocus curve. A defocus curve is a graphical representation that shows how well a patient can see at different focal distances after implantation of an intraocular lens. In simple terms, it helps us understand how a particular lens performs across different viewing distances, such as distance, intermediate, and near. To generate a defocus curve, visual acuity is measured while introducing different levels of optical defocus. Typically, after the cataract surgery, the patient is seated at a visual acuity chart and their best distance correction is first measured. Then, additional lenses are placed in front of the eye, usually in steps of about 0.5 diopters, to simulate viewing objects at different distances. In most cases, minus lenses are used to simulate closer viewing distances, while plus lenses simulate defocus in the opposite direction. At each step, the patient's visual acuity is measured and recorded. For example, minus 1.5 diopters correspond approximately to a viewing distance of about 66 centimeters, which represents intermediate vision. Minus 2.5 diopters corresponds roughly to 40 centimeters, which represents typical reading distance. Larger negative defocus values will simulate even closer near tasks. So these measurements are then plotted on a graph. On the graph, the horizontal axis represents the defocus power, which corresponds to different viewing distances, and the vertical axis represents the visual acuity. This produces the defocus curve of that intraocular lens. Different types of intraocular lenses produce characteristic patterns on these curves. A monofocal IOL typically produces a single sharp peak representing the distance at which the lens is focused, usually the distance vision. Visual acuity declines as we move away from this focal point in a monofocal IOL. In a multifocal IOL, which divides the light into multiple focal points, it produces multiple peaks on the defocus curve. For example, bifocal lenses will show 2 peaks, trifocal lenses will show you 3 peaks. Finally, the extended depth of focus lenses or the EDOF lenses, they behave differently. Instead of producing distinct peaks, they generate an elongated focal zone. So on the defocus curve, this appears as a broad plateau, indicating that the patient maintains useful vision across a continuous range of distances. Now let us begin with the simplest and most widely used intraocular lenses, the monofocal IOLs. A monofocal intraocular lens represents the most basic optical system that we implant inside the eye during cataract surgery. The term monofocal can be broken down into 2 parts. Mono means one and focal refers to the focus. So a monofocal lens is designed to create one single focal point on the retina. In most cataract surgery, this focus is set for distance vision. This means that after surgery, the distance visions will become clear. Intermediate tasks such as the computer work may require glasses, and near tasks such as reading usually require reading glasses. Now, even though premium lenses like multifocal EDOF IOLs are increasingly discussed today, it is important to understand that monofocal lenses still represent the majority of implants worldwide. The reason is simple: they provide stable, predictable, and high quality optical performance. More about that in a while. From an optical standpoint, a monofocal IOL behaves like a single refractive optical element. The entire optic of the lens has a uniform curvature and a uniform refractive power. Unlike the premium lenses, the monofocal lenses do not contain multiple optic zones. Also, they do not contain any rings. And importantly, they do not even split the light into different focal points. All the incoming light rays entering the eye are refracted by the same optical power and converge to form a single focal point on the retina. Because the light is not divided between multiple focal points, almost all the incoming light energy contributes to forming the same retinal image, and this results in 3 important optical advantages: maximum light efficiency, highest contrast sensitivity, and very minimal photic phenomena such as glare and halos. In a multifocal optical system, on the other hand, the incoming light is divided between multiple focal points. This means that each focus receives only a portion of the available light energy. So for this reason, the monofocal IOLs, because nearly all the available light contributes to a single focal point, also translates into better night vision and fewer visual disturbances. Also, monofocal IOLs for this reason are preferred in patients where contrast sensitivity is particularly important. For example, those with glaucoma, macular disease, or diabetic retinopathy. In Module 2, we discussed in detail the aspheric optics and how intraocular lenses can be designed to modify the spherical aberration. Let's now revisit that concept in the context of modern monofocal IOLs. As you know, the human cornea naturally has slightly positive spherical aberration. if we implant a standard spherical IOL with uniform curvature, it adds its own positive spherical aberration. This increases the total spherical aberration of the eye, which may slightly reduce the retinal image quality, especially under the dim light conditions when the pupil is large and peripheral rays can enter the eye. Modern monofocal IOLs have taken different optical design approaches to optimize retinal image quality. We have the negative spherical aberration lenses. These lenses introduce negative spherical aberration to compensate for the patient's positive corneal aberrations. By doing so, the total ocular aberration is minimized, improving the contrast sensitivity and image sharpness, particularly in mesopic and scotopic conditions. Example of this is the Tecnis ZCB00 lens, also referred to as the JC-BOO lens from Johnson & Johnson Vision, and it has a negative spherical aberration of minus 0.27 micrometers. The only limitation here is that if the cornea has abnormal or irregular spherical aberration, then there are chances that we might overcompensate that spherical aberration with our negative spherical aberrated lenses, and this may actually reduce the image quality. Therefore, for such conditions, we have the aberration neutral lenses. The aberration neutral lenses are designed to add zero spherical aberration, leaving the eye's natural higher order aberrations unchanged. The idea here is to preserve the patient's own aberration profile, which is particularly useful in eyes with irregular corneas or after refractive surgery. This design provides a uniform optical quality across the optic. Sometimes this is referred to as the isotropic vision, meaning that the visual quality will be consistent across the lens even with small decentrations. The examples here include the CT Asphina or the CT Lucia. These two lenses are basically from Zeiss. So the advantage is that it maintains retinal image quality without interfering with the cornea's natural optics, but limitation is that it does not reduce the positive spherical aberration in a normal cornea, maybe slightly less sharp than the negative spherical aberrated lenses in regular eyes under mesopic conditions. Okay, so remember that the aberration neutral lenses are particularly reserved for irregular corneas where you don't want to meddle with the corneal optics much. So the clinical takeaways are that the negative spherical aberrative lenses are best for patients with regular corneas seeking the maximum contrast and sharpness. The aberration neutral lenses are ideal for patients with irregular cornea, prior corneal surgery or higher order aberrations, preserving the natural optics and maintaining uniform vision quality. Both these designs reflect different optical philosophies, each aiming to optimize the retinal image while considering the individual patient's corneal profile. Before we move ahead, it is worth briefly mentioning a newer category of lenses often referred to as the enhanced monofocal IOL. These lenses are essentially an evolution of the traditional monofocal optics, where subtle modifications in the optical surface are introduced to provide a slightly extended depth of focus. Now, as a result, patients here may achieve a better intermediate vision compared to the conventional monofocal lenses, while still maintaining the excellent contrast sensitivity and very minimal photic phenomena, since the light is not being split into multiple focal points. However, it is important to understand that the enhanced monofocals represent a transition between the monofocal and extended depth of focus optics, and therefore sometimes they are also referred to as the pseudo-EDOF optical lenses, okay, or the pseudo-EDOF IOLs. For this reason, we will not go into the detailed optical mechanisms here. We will visit these lenses in much greater detail when we discuss the EDOF section of the intraocular lens. Okay, so example of enhanced monofocal lenses is the Tecnis Eyhance from Johnson & Johnson Vision and Ray-1 EMV from Rayner. Alright, coming back to the monofocal lenses. Now, even though the monofocal lenses create only a single focal point, surgeons sometimes create functional multifocality using monovision strategies. Now, in monovision, one eye is targeted for distance vision, while the other is targeted for the near vision. Typically, the refractive difference between two eyes is about 2 to 2.5 diopters. Monovision can significantly reduce dependence on reading glasses, although it may slightly reduce stereopsis as well. To minimize this issue, many surgeons use mini-monovision where the refractive difference is smaller, usually around 0.75 to 1.25 diopters. Now, this allows good distance vision while providing useful intermediate vision with less disruption of the binocular balance. So, let me tell you one important point that not every patient is happy after monovision. So, make sure you do a contact lens trial before taking up the patient for surgery. Alright, before we conclude the discussion on monofocal intraocular lenses, it is useful to briefly look at some of the commonly used monofocal IOL platforms available in clinical practice today. The purpose of discussing these lenses here is purely educational. Different surgeons may prefer different platforms based on their clinical experience, availability, and patient characteristics. The goal here is to simply help you become familiar with some of the major monofocal IOL systems and their optical design philosophies. So let us go through a few widely used examples. Let us try to understand first how decentration of an aspheric IOL leads to coma. Aspheric IOLs are designed to correct the positive spherical aberration of the cornea by inducing a negative spherical aberration. When an aspheric IOL is tilted, designed negative spherical aberration no longer perfectly compensates for the cornea's positive spherical aberration. This results in an off-axis aberration, like coma in most of the cases. Now let's start discussing the individual IOLs. The first one is Tecnis from Johnson & Johnson. The Tecnis Monofocal IOL provides full spherical aberration correction of minus 0.27 microns using the anterior surface asphericity. This will give the maximum contrast when perfectly centered. However, because the correction is on the anterior surface, even slight tilt can induce significant coma. Material-wise, it is a hydrophobic acrylic material which is modified so that it has very low glistening chances. The haptics are also modified L-shaped haptics which will provide good stability with minimal rotation. Most of the IOLs that we are going to discuss today have a 360-degree square edge to minimize the PCO formation. Next we have is the Acrisoft IQ IOL from the Alcon. Acrisoft uses minus 0.20 micron correction on the posterior surface, so slightly less compared to the Tecnis. This makes it also less sensitive to the tilt compared to the anterior design of the Tecnis. It leaves a small amount of that residual corneal aberration and that might help in the depth of field as well. Material-wise, the older versions had glistening problems, though the manufacturing now has improved. An evolution of the Acrisoft design is the Clarion or the Clarion platform, again from Alcon. It has the same optical design, but it improves the material. It uses a hydrophobic acrylic with HEMA copolymer, which increases the water content of the IOL and promotes equal distribution or a uniform distribution of water and therefore prevents glistening almost completely. So clinically, it combines Acrisoft optics with a better long-term clarity and stability compared to the Acrisoft. Both of them are from Alcon. The third one is the Vivinex platform. Vivinex is basically from Hoya Surgicals, it's a Japanese brand, and provides a correction of minus 0.18 microns correction with a unique ABC design. I will not go into the depths of the ABC design. ABC here stands for Aspheric Balance Curve Design. So very simply, it uses a dual zone to generate an opposite coma effect that will cancel each other out during the tilt. So in the center you have a spherical aberration correction, and the periphery you have an opposite coma effect, which will basically nullify the coma which will be produced in case the lens gets tilted. So this makes Vivinex highly tolerant to decentration. Then we have Envista. Envista is basically a true aberration neutral IOL, meaning it has zero spherical aberration. It basically preserves the patient's natural corneal profile, making it especially useful in post-LASIK or irregular corneas, where the corneal aberration is unpredictable and you do not really want to meddle up with it. So it's a very safe option for irregular corneas. Then we have the CT Lucia and CT Asphyna, which are basically from the Carl Zeiss Meditech platform. The CT Lucia basically uses a non-constant gradient aberration design. Here again, the center provides a mild correction of the spherical aberration, while the periphery remains almost neutral. So this makes it ideal for large pupil, so that if the paraxial rays are going to pass through that peripheral part of the lens, the aberration profile of the patient will not get altered much. So clinically, it is both pupil adaptive and also is tolerant to some amount of tilt. Then we have the CT Espina, which focuses more on the mechanical stability, and here you can see that it has plate haptics which provide 4-point fixation with extremely low rotation. It actually has a hybrid design wherein you have a hydrophilic core with a hydrophobic surface or coating. Also, the CT Espina offers different aberration options. So you have an aberration neutral option to slightly negative spherical aberration. So with that, we conclude our discussion on the monofocal intraocular lenses. We have looked at the basic concept of monofocal optics, how they introduce a single focal point, how modern lenses control spherical aberration, what is monovision and what is mini-monovision, and how some of the commonly used monofocal IOL platforms are available today. However, as we imagined, one of the main limitations of the monofocal lenses is that they provide clear vision only at one focal distance, meaning that patients will still require reading glasses for near work. To overcome this limitation, more advanced optical designs were developed that are capable of creating multiple focal points inside the eye. They are known as the multifocal intraocular lenses. In the next part of the module 3, we will begin our detailed discussion on multifocal IOLs where we will explore the optical physics behind diffraction, interference and light energy distribution and understand how modern multifocal lenses allow patients to achieve vision at multiple distances.